G'day team, welcome back to another video, and today we're going to look at two different things. We're going to look at the Bernoulli distribution and then we're going to look at the binomial distribution, and we're doing these together because the Bernoulli distribution leads very nicely into the binomial distribution. So a Bernoulli random variable x can only take two values, a 1 if a success or a 0 if a failure. Now it's really important that only one trial occurs. If you have a repeated one, then we're starting to look at binomial, but we'll talk about that in a moment. So one trial. Now we define P to be the probability of a success. So the probability that x equals 1 is P. 1 minus P is the probability of a failure. So the probability that x equals 0 is 1 take P. Now the mean, which is the expected value, is P. The variance, or sigma squared, is P times 1 minus P. And the standard deviation, sigma, is the square root of P times by 1 take P. So let's have a look at a bit of an example here. So a ball is selected from a box containing 3 red balls and 6 black balls. Let x equal 1 if the ball selected is red, x equals 0 if the ball selected is black. Explain why x is a Bernoulli random variable. Well, there is only one ball selected, so that's our one trial, and there's only two outcomes as well. So because it satisfies both conditions, it is a Bernoulli random variable. Now let's find our mean and our standard deviation. So my expected value is P. Now the probability of getting a red ball is 3 reds out of 9 total balls, or 1/3. And our standard deviation, x, is the square root of P, which is 1/3, times by 1 take P, which is 2/3. So that's going to be the square root of 2/3. So by the time you expand and simplify our surd, we get square root of 2/3. So really not too difficult, but what happens is when we repeat that Bernoulli variable, we start looking at a binomial distribution. Now, really important for a binomial random variable x, the total number of successes in n independent trials. So that word independent is really important. One trial can't affect the probability of the next trial. And like I said, it's a repeated Bernoulli experiment. So an experiment with two possible results, a success or a failure. Now again, P is our success, 1 take P is a failure, and for n independent trials and k successes, so that means n take k failures, we can actually use our general term formula for a binomial expansion. And we looked at that in year 11 methods. So the probability that x equals k is the combination n choose k. P is my success probability to the power of k, which is the number of successes, times 1 take P to the power of n take k. So the probability that x equals k is the binomial probability distribution function, and we define it to be x is distributed binomially with n trials and success P. So that weird sort of line, squiggly line there reads is distributed as. When we get to continuous variables, we'll use that language and notation again. So let's have a look at an example. So we're going to expand 6/7 plus 1/7 to the power of 4. Then we get into a bit of a context of a pill has a 6 in 7 chance of successfully stopping bacteria. Find the probability of a few different things. Now this is taking us back to 11 methods again, and we're going to need Pascal's triangle. So let's just do a quick Pascal's triangle, and we need 4 lines. So they're going to be our coefficients. So let's start with 6/7 to the power of 4 plus 4 times 6/7 to the power of 3. 1/7 is my probability of a failure, plus 6/7 to 1/7, 2 plus 4, 6/7, 1/7, 3 plus 1/7 to the power of 4. So that is my binomial expansion there. So the probability that one pill exactly works out of 4 pills. Well, we've got our number of pills 4. So we can use these terms to find our probabilities. So the probability that X equals 1 pill, I need to find where K equals 1. So I need the first bracket to have a power of 1, which is this term here. So that's going to be 4. 6 over 7 to the power of 1, 1 over 7 to the power of 3. Now, I've got my calculator next to me, so I'm just going to quickly do this sum. 6 over 7 times 1 over 7 to the power of 3. And I get, so that's equal to 0.00996. Okay, so a very small percentage that only one of them works. At least 3 pills work, so the probability that X is greater than or equal to 3. Now with binomial, we can't sort of just do it as it is. We need to look at all the scores. So this is the same as the probability that X is equal to 3 plus the probability that X is equal to 4. So the 2 outcomes that give us what we want. So now I look for, where does my powers have 3 and 4 in the first bracket? Well, I've got this term for 4 and this term for 3. So I'll write 3 in first. 4 times 6 over 7 to the power of 3, 1 over 7 to the power of 1, plus 6 over 7 to the power of 4 for 4 pills working. So I'll go in and calculate this. Got to the power of 3 there. 1 over 7 to the power of 1 plus 6 over 7 to the power of 4, which gives me 0.999, can't read a calculator, 8996 as my probability. Okay, so very high chance that at least 3 pills work. Then the probabilities that the first 2 pills work, so that's the probability of working, not working, which we can just simply do by multiplying our probabilities together. It's conditional probability. So I've got 6 over 7 times 6 over 7 for the 2 working, and 1 over 7 squared for the 2 not working. So quickly put this into the calculator. 6 over 7 to the power of 2 times 1 over 7, also to the power of 2, and I get out approximately 0.01499 as my probability. Okay, so just be careful, have to have whole numbers, and we can use our binomial expansion. So thank you guys for watching, and we'll catch you in the next video.